There's a galaxy out there so enormous that our entire Milky Way would be nothing more than a speck inside it. We're talking about a structure so vast that 140 of our galaxies could line up end to end and still not match its length. But here's what makes this discovery truly unsettling. We almost missed it entirely. In 2024, astronomers spotted something that shouldn't exist. At least, not according to what we thought we knew about how galaxies form and grow. The galaxy is called Porphyrion, and it stretches across 23 million light-years of space. To put that in perspective, the distance from Earth to the nearest major galaxy, Andromeda, is only 2.5 million light-years. Porphyrion is nearly 10 times that distance from end to end. What you're about to discover will fundamentally change how you think about the universe's architecture, because Porphyrion isn't just big. It's revealing something profound about the invisible forces that shaped everything we see in the cosmos today. Let's start with a question that seems simple but isn't. What exactly is a galaxy? You probably picture a massive collection of stars, right? Hundreds of billions of suns spinning together in space, held by gravity. That's accurate, but it's only part of the story. Galaxies are more like cosmic ecosystems. They contain stars, sure, but also planets, gas clouds, dust, dark matter, and at their centers, something far stranger. Nearly every large galaxy harbors a supermassive black hole at its core. These aren't the stellar mass black holes formed from collapsing stars. We're talking about monsters containing millions or billions of times the Sun's mass, compressed into a region smaller than our solar system. Our Milky Way has one. It's called Sagittarius A star, and it weighs about 4 million times what the Sun does. That sounds massive until you compare it to the heavyweight champions. Some supermassive black holes tip the scales at 20 billion solar masses or more. Now here's where it gets interesting. These black holes aren't just sitting there passively. When matter falls toward them, it doesn't simply disappear. The material forms an accretion disk, a swirling maelstrom of superheated gas that glows brighter than billions of stars. And sometimes, in ways we're still trying to fully understand, these black holes launch jets. Picture two narrow beams of material and energy, shooting out from opposite sides of the black hole at nearly the speed of light. These jets can extend far beyond the galaxy itself, punching through intergalactic space for millions of light years. The energy involved is staggering. We're talking about power outputs equivalent to trillions of suns. Galaxies that produce these enormous jets are called radio galaxies, because the jets emit strongly in radio wavelengths. When astronomers first started discovering them in the mid-20th century, they thought these structures were rare oddities, cosmic freaks that occasionally popped up in the universe. They were wrong. Using modern radio telescopes, especially Europe's LOFAR array, astronomers have found over 10,000 of these jet systems. They're not rare at all. They're just incredibly faint and difficult to detect, which means we've been looking at a universe with a major component we barely understood. But even among these thousands of radio galaxies, a special category stands out. Scientists call them giant radio galaxies, or GRGs. These are the titans, the record breakers, the ones that make other galaxies look small. To qualify as a giant radio galaxy, your jets need to extend at least 0.7 megaparsecs from end to end. That's roughly 2.3 million light years. To give you a sense of scale, That's about the distance from the Milky Way to Andromeda. Imagine jets so powerful they could cross that entire gulf of intergalactic space. For decades, finding these giants was like searching for needles in a cosmic haystack. Radio surveys had to cover enormous sections of sky with enough sensitivity to detect these faint structures. The technology simply wasn't there. But in the last few years, that's changed dramatically. In February 2022, a team led by astronomer Martijn Oe announced the discovery of Alcyoneus, located 3.5 billion light-years away in the constellation Lynx. Its jets stretched an incredible 16 million light-years across. That's 5 megaparsecs, 100 Milky Way galaxies laid end to end. The astronomical community was stunned. How could jets remain stable and coherent across such vast distances? What was powering them? Why hadn't we seen anything like this before? The answer to that last question was simple. We had seen them. We just didn't recognize what we were looking at. Alcyoneus had been sitting in radio survey data for years. It took new processing techniques and, frankly, just staring at the images long enough for the human eye to pick out the faint patterns. But here's the thing about records in astronomy. They don't last long. Within months, astronomers found SDSSJ 0819 5 6.4 1 plus 3 2 3 5 3 7.6, a galaxy with jets spanning 17 million light-years. Then came others. The discoveries started accelerating. Each new survey seemed to reveal structures that pushed the boundaries of what we thought possible. And then in 2024, the team analyzing LOFAR data found Porphyrion. At first, it looked like just another radio galaxy, a bright dot in the constellation Draco, surrounded by the telltale lobes of radio emission. But as the researchers traced the structure outward, they realized they were looking at something unprecedented. The jets extended and extended, past 1 megaparsec, past 2, past 5. When they finally mapped the full extent, the numbers seemed almost absurd. 7 megaparsecs, 23 million light-years from end to end. To help your brain process that distance, consider this. The Milky Way is about 100,000 light-years across. Porphyrion's jets are 230 times that diameter. If you could shrink Porphyrion down so its jets spanned the length of a football field, the Milky Way would be about 5 inches long. Earth's entire orbit around the Sun would be smaller than a grain of sand. But the size was only the beginning of the mystery. Porphyrion's jets originated from a galaxy 7.5 billion light-years away. That means we're seeing it as it was 7.5 billion years ago, when the universe was less than half its current age. The cosmos was smaller then, more compact, with the large-scale structure of galaxies and galaxy clusters still taking shape. Here's what makes that timing significant. At that epoch in cosmic history, the universe's structure was different. The cosmic web, that vast network of dark matter filaments connecting galaxy clusters, had its threads packed closer together. Calculations show that Porphyrion's jets span roughly 2/3 the distance across the cosmic voids between these filaments. Think about what that means. This single object, powered by a black hole in one galaxy, was reaching across a significant fraction of the universe's large-scale structure. It wasn't just big, it was cosmological in scale. When Martijn Oe's team published their findings, they were careful to verify everything. Multiple telescopes confirmed the measurements. The giant meter-wave radio telescope in India helped pinpoint the host galaxy. data from the Dark Energy Spectroscopic Instrument provided additional confirmation. The host galaxy itself turned out to be surprisingly normal, about 10 times more massive than the Milky Way, which sounds huge until you realize that many giant radio galaxies come from even larger hosts. The supermassive black hole at its center weighs in at around 400 million solar masses. Hefty certainly, but not exceptional. That ordinariness was actually the most confusing part. If Porphyrion came from such a relatively normal galaxy, why were its jets so much larger than everything else? What allowed them to grow to such extreme sizes? The answer might lie in something called jet stability. For jets to extend across millions of light years without breaking apart or dissipating, they need to remain remarkably stable over enormous timescales. We're talking about 1 billion years or more of continuous, steady output from the central black hole. Most black holes don't stay active that long. They go through feeding cycles. Material falls in, jets fire, then the supply of gas runs out and everything shuts down. The jets fade. But Porphyrion required something different. An unusually long-lived stable accretion event. The black hole needed to feed continuously for roughly 1 billion years, with the jets maintaining the same direction and power output the entire time. Any significant variation, any wobble in the jet direction, would have disrupted the structure. Nobody knows exactly how that happens. It might have to do with the galaxy's environment. Porphyrion sits embedded in a filament of the cosmic web, surrounded by streams of gas flowing through intergalactic space. Perhaps that provided a steady fuel supply. Or maybe the black hole's spin and magnetic field configuration were perfectly aligned to maintain stable jets. What we do know is this: Porphyrion isn't alone. Shortly after its discovery, astronomers started finding more extreme giants. In late 2024, they identified TXS 0033+252, a radio galaxy with jets extending approximately 26 million light-years. The record had been broken again, but calling these objects galaxies creates a problem. When most people hear that word, they think of stars. Billions of stars clustered together. And by that measure, Porphyrion isn't even in the top 100 largest galaxies. The visible galaxy at its center, the part made of stars, is fairly ordinary in size. The jets are something else entirely. They're not made of stars. They're streams of plasma and magnetic fields carrying energy at relativistic speeds through the near vacuum of intergalactic space. Calling the entire structure a galaxy is technically misleading. This is why you'll sometimes see Porphyrion described as having the largest radio structure, rather than being the largest galaxy. It's a semantic distinction, but an important one. Different types of measurements give different answers to the question of what's biggest. If we're measuring by stellar content, the actual stars and gas that make up the visible part of a galaxy, the title probably goes to IC 1101. This supergiant elliptical galaxy sits at the center of the Able 2029 galaxy cluster, about 1.15 billion light-years from Earth. IC 1101 spans somewhere between 400,000 and 550,000 light-years across, depending on how you measure it. That's roughly 4 times the Milky Way's diameter. But its extended halo of faint light reaches even farther, potentially out to 2 million light-years. The galaxy contains an estimated 100 trillion stars. Let that number sink in. Our galaxy has maybe 400 billion stars. and that already seems incomprehensible. IC1101 has 250 times more. At its center lurks one of the largest black holes known, surrounded by a core region larger than the cores of other giant ellipticals. How did IC1101 grow so massive? The answer is collisions. Lots and lots of collisions. Galaxy mergers are common in dense galaxy clusters, and IC1101 sits at the gravitational center of its cluster. Over billions of years, it's cannibalized dozens, possibly hundreds of smaller galaxies that wandered too close. Each collision strips away gas and dust while adding stars to the growing giant. The violent interactions trigger bursts of star formation initially, but eventually, all the gas gets used up or blown away. What remains is a bloated elliptical galaxy filled with ancient stars, growing ever larger but forming fewer new suns. This is the fate awaiting many galaxies in dense clusters. They'll merge and merge again until a single massive elliptical dominates the center. In a sense, IC1101 represents the endpoint of galactic evolution in crowded environments. But it raises a question. If IC1101 is the largest by stellar content, and Porphyrion is the largest by radio structure, which one is truly bigger, and does that question even make sense? The answer depends on what you think a galaxy fundamentally is. Is it the stars? Is it the dark matter halo surrounding those stars? Is it everything influenced by the central black hole, including jets that extend for millions of light years? There's no universal agreement. Different astronomers emphasize different aspects. What's becoming clear, though, is that our old definitions are breaking down. The universe is revealing structures that don't fit neatly into the categories we created, and Porphyrion is forcing us to confront something even more profound about the cosmos, something that goes beyond just measuring size, because those massive jets didn't just exist in isolation. They were actively shaping the universe around them. Those jets stretched across 23 million light-years of space. To put that in perspective, they were pumping energy and magnetic fields into a volume that contained thousands of other galaxies. This wasn't just a single galaxy growing massive. This was a single black hole, fundamentally altering the properties of an entire region of the universe. Think about what that means. The space between galaxies isn't truly empty. It's filled with incredibly thin gas, the intergalactic medium, which consists mostly of hydrogen left over from the Big Bang. This gas is so sparse that it barely qualifies as a substance by our everyday standards. We're talking about densities far lower than any vacuum we can create on Earth. Yet it's there, and it fills the gaps between galaxies. When Porphyrion's jets plowed through this medium, they didn't just pass through it harmlessly. They heated it, energized it, magnetized it. The jets carried powerful magnetic fields wound up near the black hole, and as they traveled outward, they deposited those fields into the intergalactic medium. Before the jets arrived, that gas might have been relatively field-free. After they passed, it was threaded with magnetism. Why does this matter? Because magnetic fields affect how gas behaves. They influence how it clumps together, how it cools, how it eventually collapses to form new stars and galaxies. Porphyrion's jets weren't just big. They were cosmic engineers, reshaping the conditions across millions of light years of space. And here's where it gets more profound. The universe Porphyrion lived in was different from ours. The jets existed when the cosmos was only 6.3 billion years old, less than half its current age. Back then, the universe was smaller, denser, more compact. The cosmic web, that vast network of filaments and voids that gives the universe its large-scale structure, was tighter. The strands were closer together. Calculations show that Porphyrion's jets reach 2/3 of the way across the cosmic voids between filaments. That's not just impressive by galactic standards, that's cosmological. The jets were interacting with the fundamental architecture of the universe itself, touching the very scaffolding on which galaxies form and evolve. And here's what researchers are starting to realize. Porphyrion probably wasn't unique. Giant radio galaxies like this should have been far more common in the early universe. Black holes were more active back then. Gas was more abundant. The conditions were ripe for massive jet production. If Porphyrion could reach 2/3 across cosmic voids, and if there were many objects like it, then these jets might have magnetized the entire intergalactic medium. That would explain something that's puzzled astronomers for years. When we observe the space between galaxies today, we find magnetic fields. Not strong ones, but they're there. We've never fully understood where those fields came from. Were they left over from the Big Bang? Did they grow from seed fields through some amplification process? The discovery of giant radio galaxies offers a simpler explanation. Black hole jets sprayed magnetism throughout the cosmos billions of years ago. Every place in the universe, researchers now suspect, has been touched by black hole activity at some point. Not directly, but through these enormous jets that stretched across cosmic distances when the universe was young. Your location in space, right now, probably once fell within the influence zone of some ancient jet system. This completely changes how we think about galaxy evolution. We used to imagine galaxies as relatively isolated islands, evolving mostly through their own internal processes. Mergers happened, sure, but they were discrete events. Gas fell in from the cosmic web, but gradually. The picture was one of bottom-up growth, small structures merging to form larger ones. But if black hole jets could reach across millions of light years, affecting the properties of gas across entire cosmic voids, then galaxies weren't isolated at all. They were connected through these powerful outflows. A black hole in one galaxy could influence star formation in galaxies millions of light years away by altering the temperature, density, and magnetic properties of the gas between them. Astronomers call this feedback. Black holes don't just consume matter, they also regulate how much new matter can form into stars. They act as cosmic thermostats, heating gas to prevent it from collapsing too quickly. This feedback is crucial for explaining why galaxies aren't more massive than they are. Without it, theoretical models predict that galaxies would convert far more of their gas into stars, growing much larger than we observe. But most feedback models focus on the local effects within a single galaxy or galaxy cluster. Porphyrion is showing us that feedback can operate on much larger scales. The jets from one galaxy's black hole can affect the evolution of hundreds or thousands of neighboring galaxies by altering the properties of the cosmic web itself. Now, you might be wondering how we even found Porphyrion in the first place. Radio astronomy has come a long way, but detecting faint radio emissions from structures millions of light years across isn't easy. The breakthrough came from LOFAR, the Low Frequency Array, a network of radio telescopes spread across Europe. LOFAR specializes in detecting low-frequency radio waves, exactly the kind emitted by these giant lobes. Previous radio surveys had the resolution to see small details but missed large-scale structures. or they had wide coverage but lacked sensitivity. LOFAR changed the game by combining high sensitivity with the ability to image large structures without washing them out. The survey that found Porphyrion has revealed more than 10,000 giant radio galaxies. 10,000. These objects aren't rare anomalies. They're a significant population. Most of them are smaller than Porphyrion, but not by much. We're talking about jets that routinely span several million light-years. The sheer number of these systems suggests that the universe has been saturated with black hole energy output over cosmic time. And because we're seeing these systems at various distances, we're looking at different epochs in cosmic history. We can trace how common they were at different times. What researchers found is striking. Giant radio galaxies were more common in the past. When the universe was younger and more compact, conditions favored the growth of these enormous jet systems. As the universe expanded and galaxies spread apart, as gas became more sparse and black holes became less active, the giants became rarer. This fits with what we know about quasars, the most luminous active black holes. Quasars were far more common when the universe was between 1 and 3 billion years old. That was the epoch of peak black hole growth, when supermassive black holes were gorging on gas and shining with the light of trillions of suns. Many of those quasars would have been launching jets. Some of those jets would have grown to cosmological scales. Porphyrion comes from a time when the universe was 6.3 billion years old, past the peak quasar era, but still relatively young. Its host galaxy is about 10 times the mass of the Milky Way, substantial but not exceptional. The black hole at its center isn't record-breaking either. What makes Porphyrion special isn't the properties of its host galaxy or black hole. It's the stability and longevity of its jets. For jets to reach 23 million light-years, they need to stay active for an incredibly long time. Roughly 1 billion years. That's 1/10 of the current age of the universe. The black hole needs to maintain a steady diet of infalling matter for all that time, and the jets need to keep pointing in the same direction without destabilizing or shutting off. That's harder than it sounds. Black holes are messy eaters. The accretion disk, the swirling maelstrom of matter spiraling into the black hole, is turbulent and chaotic. Jets can flicker on and off. They can change direction if the black hole's spin axis shifts. For a system like Porphyrion to maintain such long-lived, stable jets suggests something special about its feeding mechanism. One possibility is that the black hole is fed by a steady stream from the cosmic web. The host galaxy sits embedded in a filament, one of those dense strands of dark matter and gas that connect galaxies. If gas is flowing along that filament directly toward the black hole, it could provide a sustained fuel supply without the chaos of a major galaxy merger. Another intriguing detail is that Porphyrion's black hole is what's called a radiative mode black hole. This is different from the jet mode black holes that power most giant radio galaxies. Radiative mode black holes are more efficient at converting infalling matter into radiation. They shine brighter in visible and ultraviolet light. Astronomers didn't think they could produce jets as large as Porphyrion's. The fact that they can has implications. Radiative mode black holes were more common in the early universe. If they're capable of launching giant jets, then the early cosmos might have been even more dominated by these massive outflows than we thought. The influence of black holes on galaxy evolution and the intergalactic medium might have been even more profound. There's also the question of what happens when these jets finally shut off. The lobes don't just disappear, they fade gradually as the high-energy particles lose energy through radiation and collisions. But the magnetic fields they've deposited into the intergalactic medium remain. Those fields can persist for billions of years, long after the jets that created them have gone silent. So, when we observe magnetic fields in the space between galaxies today, we might be seeing the fossil remnants of jets that were active billions of years ago. The universe has a memory. The structures we see now carry the imprint of processes that happened long ago in cosmic time. This brings us back to the question of what makes a galaxy big. Porphyrion's host galaxy isn't particularly massive. Its stellar content is unremarkable, but its influence, the volume of space it has affected through its jets, is cosmological. In a real sense, Porphyrion is one of the largest structures associated with a single galaxy that we've ever observed. Not because the galaxy itself is huge, but because its reach extends across an almost incomprehensible expanse. And we're only just beginning to understand what that means for the evolution of the universe as a whole. The discovery of structures like Porphyrion fundamentally changes how we think about the scale of individual galactic influence. But it also raises an uncomfortable question. How many of these monsters are we missing? When Martin Oe and his team first spotted Porphyrion in LOFAR data, they weren't specifically hunting for record breakers. They were conducting a systematic survey, combing through radio observations of the sky looking for giant radio galaxies in general. What they found was shocking. More than 10,000 of these massive jet systems. Not dozens, not hundreds, thousands. This wasn't because giant radio galaxies suddenly appeared. They were there all along, we just couldn't see them. The problem is technical, but it's worth understanding because it tells us something profound about the limits of our knowledge. Radio telescopes work by detecting electromagnetic radiation at wavelengths much longer than visible light. Different surveys use different frequencies and have different sensitivities. The NVSS, the NRAOVLA Sky Survey, had been around for decades. It's coarse. It sees the bright stuff but misses faint, diffuse structures. The first survey has better resolution. It can pinpoint the cause of galaxies and identify where the jets originate. But it sacrifices sensitivity to large-scale structures in exchange for that precision. LOFAR is different. It operates at lower frequencies and has been optimized to detect both fine details and extended, faint emissions. When researchers reprocessed LOFAR data specifically looking for giant radio galaxies, they found structures that had been invisible in previous surveys. Alcyoneus, the former record holder, was hiding in plain sight. Its lobes are faint. They stretch across such a vast area that earlier instruments either couldn't detect them or mistakenly classified them as separate objects. Porphyrion was even harder to spot. The team used LOFAR's capabilities to map the diffuse radio emission across enormous swaths of sky. Then they did something old-fashioned. They looked at the images with their own eyes. Pattern recognition, human intuition. Because sometimes the best tool for finding something unexpected is just careful attention. What they discovered suggests we've been systematically underestimating the population of giant radio galaxies. These objects aren't rare anomalies, they're common. The universe has been producing them throughout cosmic history, and we're only now beginning to compile a complete census. This has implications that ripple outward through cosmology. If giant radio galaxies are common, Their collective impact on the intergalactic medium is far greater than we thought. They're not isolated phenomena affecting small regions of space. They're a major player in shaping the large-scale environment of the universe. Consider the energy budget. Each of these jets carries the power output of trillions of suns. Multiply that by thousands of active systems at any given time, and you're talking about an enormous injection of energy into the space between galaxies. That energy heats gas. It drives turbulence. It creates magnetic fields that persist long after the jets shut off. This matters for galaxy formation. Gas needs to cool and collapse to form stars. But if that gas is constantly being heated by energy from jets, it stays diffuse and hot. Star formation gets suppressed. Galaxies grow more slowly. The jets act as a cosmic thermostat, regulating how efficiently the universe can convert gas into stars. There's also the magnetism. Space between galaxies isn't empty. It's filled with an extremely thin plasma, ionized gas at temperatures of millions of degrees, and observations show this plasma is magnetized, not strongly, but measurably. Where do those magnetic fields come from? Giant jets are a leading candidate. As they plow through the intergalactic medium, they drag magnetic fields along with them. The jets twist and tangle the fields into complex structures. Even after the jets fade, those fields remain, threaded through the cosmic web like invisible filaments connecting galaxies across vast distances. This magnetization has consequences. Magnetic fields affect how cosmic rays propagate. They influence the behavior of plasma in galaxy clusters. They may even play a role in the formation of the first stars by affecting how primordial gas clouds collapse. Porphyrion's existence in the early universe is particularly revealing. At a redshift corresponding to when the universe was 6.3 billion years old, the cosmic web was more compact. Filaments of dark matter and gas were closer together. Voids between them were smaller. Porphyrion's jets stretched 2/3 of the way across a typical void at that epoch. They're not confined to their host galaxy or even their local neighborhood. They're reaching across cosmological distances, directly connecting one filament of the cosmic web to another. What does this mean? It suggests that black hole jets were actively mixing material across the cosmic web during a critical period of galaxy evolution. Gas flowing along filaments could be heated or magnetized by jets from galaxies it had never directly interacted with. The large-scale structure of the universe wasn't just a passive backdrop for galaxy formation. It was being actively shaped by the most energetic processes occurring within galaxies themselves. This feedback loop between galaxies and their environment is something astronomers have been trying to understand for decades. Simulations of galaxy formation consistently predict too many stars forming too early, unless you include some mechanism to slow things down. Jets from supermassive black holes are one of the most promising candidates for that mechanism. But until recently, we thought their influence was mostly local, confined to the immediate surroundings of the host galaxy. Giant radio galaxies like Porphyrion demonstrate that this picture is incomplete. The influence isn't local, it's cosmological. Jets can affect regions of space far larger than the galaxies that produce them. There's a philosophical dimension to this as well. We tend to think of galaxies as discrete objects, islands of stars separated by vast gulfs of empty space. But the discovery of these enormous jet systems blurs that distinction. Where does a galaxy end and intergalactic space begin? If a galaxy's black hole is actively shaping the environment hundreds of millions of light years away, is that region not, in some sense, part of the galaxy's sphere of influence? This is where the definition of largest galaxy becomes genuinely murky. IC 1101, with its 4 to 6 million light-year diameter of stars, is enormous by traditional measures. Its stellar content is unmatched, but its direct influence on the surrounding universe is limited to its immediate gravitational reach. Porphyrion's host galaxy, by contrast, is unremarkable in terms of stellar mass. It's about 10 times the mass of the Milky Way. Hefty, but not extraordinary. Yet its jets extend across 23 million light-years, and their effects, the heating, the magnetization, the turbulence they induce, may propagate even farther. Which is larger, the galaxy with more stars, or the galaxy with greater reach? This isn't just semantic hair-splitting. It reflects a genuine uncertainty about how we should think about galactic influence in a universe where the most powerful processes can operate across scales that dwarf the galaxies themselves. The recent discovery of TXS 0033+252, with jets estimated to span 26 million light-years, pushes this even further. Each new record holder forces us to recalibrate our understanding of what's possible. And given that we've only surveyed a fraction of the sky at the sensitivity needed to detect these structures, there are almost certainly larger systems waiting to be found. Australia's Square Kilometre Array Pathfinder recently turned up 15 new giant radio galaxies in a single field of view, including one with lobes stretching 12.4 million light-years. These weren't found through years of painstaking observation. They emerged from a routine survey of a relatively small patch of sky. Scale that up to the entire observable universe, and the numbers become staggering. There could be hundreds of thousands of giant radio galaxies, maybe millions, each one reshaping its local environment, each one contributing to the collective process of heating, magnetizing, and stirring the intergalactic medium. One particularly intriguing discovery in that Australian survey was ASCAP J 0107-2347. It shows a nested structure, 2 sets of lobes, one inside the other. The inner lobes are bright and compact. The outer lobes are faint and elongated. This suggests episodes of activity separated by periods of quiescence. The black hole turned on, launched jets, then shut off. Later, it reactivated and launched a new set of jets. This on-again, off-again behavior might be key to understanding how these systems grow so large. Instead of one continuous billion-year feeding event, maybe giant radio galaxies undergo multiple shorter bursts of activity. Each burst extends the jets a bit farther. Over time, through repeated cycles, the lobes grow to enormous sizes. This would solve one of the puzzles. How do these systems maintain stable jets for so long? Maybe they don't. Maybe the jets flicker on and off, and what we're seeing is the cumulative result of many separate episodes of activity. If that's true, then the fossil lobes we observe today might contain a record of the black hole's feeding history, written in the structure of the radio emission. Bright regions where fresh material was recently injected. Faint regions where older material has been slowly fading for millions of years. Gaps or distortions where the jets changed direction during periods of inactivity. This is still speculative, but it points to a richer, more complex picture of how these systems evolve, and it suggests that future observations with even more sensitive instruments will reveal layers of structure and history that we're currently missing. The deeper we look, the more we find. And every discovery raises new questions. Why are some black holes able to produce such enormous jets, while others, seemingly similar in mass and feeding rate, produce much smaller structures? Is it something about the black hole's spin, the properties of the surrounding gas, the orientation of the magnetic field in the accretion disk? We don't know. The physics of jet launching is still not fully understood, despite decades of theoretical work and observation. We know that strong magnetic fields are involved. We know that the black hole's rotation plays a role, but the precise mechanism that converts the rotational energy of a spinning black hole into a tightly collimated beam of particles moving at near light speed remains one of the great unsolved problems in astrophysics. Giant radio galaxies like Porphyrion give us a laboratory to test ideas. Their sheer size means we can study the jets far from the chaotic environment of the galactic core. We can see how they interact with different densities of intergalactic gas. We can measure how they lose energy over distance. We can trace the structure of the magnetic fields they create. Each new observation adds a piece to the puzzle. And as the census of giant radio galaxies grows, patterns are beginning to emerge. One pattern is that these systems don't seem to require anything exotic. The host galaxies aren't unusually massive. The black holes aren't extraordinarily large. The environments aren't particularly special. This is both reassuring and perplexing. Reassuring because it means we don't need to invoke rare or extreme conditions. Perplexing because if these systems are so normal, why don't all radio galaxies grow to such enormous sizes? The answer probably lies in timing and stability. Most jets don't remain active long enough. Most feeding events are disrupted by galaxy mergers or other environmental changes before the jets can grow to cosmological scales. Giant radio galaxies represent a fortunate combination of circumstances: a steady fuel supply, a stable jet orientation, and an environment with low enough density that the jets can propagate without being disrupted. But as we continue to find more of these systems, it's becoming clear that this fortunate combination isn't as rare as we once thought. The LOFAR Discovery changed everything. Before this telescope array came online, astronomers had found maybe a few hundred giant radio galaxies total. Now, they're discovering them by the thousands. More than 10,000 of these systems have been identified in LOFAR surveys alone. This isn't because giant radio galaxies suddenly became more common. It's because we finally built an instrument sensitive enough to see them. LOFAR operates at low frequencies, between 30 and 240 megahertz. These are radio waves with wavelengths several meters long. At these frequencies, the telescope can detect extremely faint, diffuse emission that higher frequency instruments completely miss. The older surveys, like NVSS and FIRST, either lacked the resolution to see fine details or the sensitivity to pick up faint extended structures. LOFAR combines both: high resolution and high sensitivity. It can resolve the cause of distant galaxies while simultaneously mapping the enormous, faint lobes stretching millions of light years away. The survey that found Porphyrion covered a significant fraction of the northern sky. Researchers generated images representing the most sensitive search ever conducted for radio galaxy lobes. But even with all that technology, The actual discovery method was decidedly analog. Human eyes. Pattern recognition software can help, but there's something about the human visual system that's exceptionally good at picking out subtle patterns in noisy data. Researchers scrolled through image after image, looking for the telltale signs of giant lobes. And that's how they found it. A faint, extended structure stretching across an impossible distance. Finding the structure was one thing. Identifying its source galaxy was another challenge entirely. Radio lobes don't come with address labels. You have to work backward from the structure to pinpoint the exact galaxy responsible. For Porphyrion, this required follow-up observations with the giant meter-wave radio telescope in India, combined with optical data from the Dark Energy Spectroscopic Instrument. The GMRT provided higher resolution radio data that could trace the jets back to their origin point. DESI provided spectroscopic information that confirmed the galaxy's distance and properties. What they found was surprising. The host galaxy sits 7.5 billion light-years away. It's hefty, about 10 times the mass of the Milky Way, but not extraordinarily so. The black hole at its center is probably several hundred million solar masses. Large, but again, not exceptional by the standards of supermassive black holes. Nothing about this system screams record breaker, except for the jets themselves. This raises a critical question that researchers are still grappling with. If Porphyrion's host galaxy and black hole are relatively normal, what allowed it to produce such extraordinary jets? One possibility involves the cosmic web itself. The universe isn't uniform. Matter clusters along filaments of dark matter that stretch across hundreds of millions of light-years, creating a web-like structure on the largest scales. The nodes where filaments intersect become the sites of galaxy clusters. The filaments themselves act as highways along which gas flows, feeding galaxies and their central black holes. Porphyrion's host galaxy appears to be embedded in one of these filaments. The jets align roughly with the filament's orientation. This might not be coincidental. If the jets are propagating along a cosmic filament, they're moving through a channel where the density of intergalactic gas varies in a structured way. Lower density in some regions, higher in others, but with an overall pattern that could guide the jets and help them maintain their structure over enormous distances. But here's what makes this particularly intriguing. Porphyrion existed when the universe was only 6.3 billion years old. At that epoch, the cosmic web was more compact. Filaments were closer together. Voids between filaments were smaller. This means Porphyrion's jets, spanning 23 million light-years, reached across a greater fraction of the cosmic web than similar-sized jets would today. Calculations suggest the jets extended about 2/3 of the way across the typical void between filaments at that time. They were genuinely cosmological in scale, touching multiple large-scale structures. This has implications that go beyond just being a record holder. If jets this large were common in the early universe, and if they regularly extended across significant fractions of the cosmic web, they could have played a major role in shaping galactic evolution on the largest scales. Every place in the universe might have been affected by black hole jet activity at some point in cosmic history. The energy these jets carry, the magnetic fields they create, the heating they produce in the intergalactic medium, all of this could have influenced how galaxies formed and evolved across billions of light years. Consider the energy budget. A single giant radio galaxy represents a sustained output equivalent to trillions of suns, maintained for tens or hundreds of millions of years. That energy has to go somewhere. Some of it goes into accelerating particles to nearly the speed of light. Some heats the surrounding gas. Some generates magnetic fields that pervade the intergalactic medium. And because these jets extend so far, they deposit this energy across truly vast volumes of space. The intergalactic medium today is magnetized. Observations show that even in the emptiest regions between galaxies, there are weak magnetic fields. Where did these fields come from? One leading hypothesis is that they were created and amplified by jets from active galaxies. If systems like Porphyrion were common in the early universe, their jets could have seeded magnetic fields throughout the cosmic web. As the universe expanded and evolved, these seed fields grew and spread, eventually creating the magnetized cosmos we observe today. There's another consequence worth considering. Jets inject turbulence into the intergalactic medium. They create shock waves, compress gas, and generate complex flows. This turbulence affects how gas cools and collapses to form new galaxies. Too much heating, and gas can't cool efficiently, suppressing galaxy formation. Just the right amount, and you might enhance star formation in certain regions, while suppressing it in others, creating the diverse population of galaxies we see today. The discovery of systems like Porphyrion forces us to think about black hole feedback on entirely new scales. For years, astronomers have focused on how black holes affect their immediate surroundings, the central regions of galaxies, maybe the galaxy cluster if it's a particularly powerful system. But jets spanning 23 million light-years reach far beyond any single galaxy or cluster. They touch multiple structures. They affect regions that have no direct gravitational connection to the host galaxy. This is feedback operating on cosmological scales. And if it was common in the early universe, we need to incorporate it into our models of cosmic structure formation. Current simulations of galaxy evolution include black hole feedback, but they typically focus on smaller scales. Jets that extend a few 100,000 light-years, maybe a million or two. Not jets that span dozens of megaparsecs. Adding these enormous systems to simulations might change predictions for how galaxies and large-scale structure evolved. But there's a catch. We don't yet know how common systems like Porphyrion actually were. LOFAR is finding thousands of giant radio galaxies, yes, but most of them are smaller than Porphyrion. The truly enormous ones, spanning more than 5 or 7 megaparsecs, are still relatively rare in the data. Is this because they're genuinely rare, or because they're so faint and diffuse that we're only detecting the brightest examples? The answer matters. If systems like Porphyrion were 1 in a million, their impact on cosmic evolution would be limited. Interesting, but not transformative. But if they were 1 in 1,000, or even 1 in 100, then nearly every region of space would have been affected by jets at some point. The cumulative effect would be enormous. And the fact that we're finding more of these systems every time we look deeper suggests they might be more common than we initially thought. There's also the question of evolution. The giant radio galaxies we observe today are fossils. The jets shut off long ago, and what we're seeing is the fading afterglow. But how long does it take for these structures to fade completely? If a jet shuts off, the lobes don't immediately disappear. They continue to emit radio waves as the particles gradually lose energy. This fading process takes time, millions of years, perhaps tens of millions. During that time, the structure remains visible to radio telescopes. This means the population of giant radio galaxies we observe includes both active systems, where the jets are still being fed, and fossil systems, where the activity has ceased but the structure hasn't yet faded. Distinguishing between these two populations is difficult. Some systems show clear signs of ongoing activity, bright hotspots where fresh material is being injected, compact cores with strong emission. Others are faint and diffuse, with no obvious hotspots or cores, suggesting the jets have been off for a while. Understanding the ratio of active to fossil systems helps us estimate how long these jets typically remain active. If most of the giant radio galaxies we observe are fossils, it suggests that the active phase is relatively brief, perhaps only 10 or 20 million years, followed by a much longer fading phase. If most are still active, it suggests the jets can maintain themselves for much longer periods, perhaps 100 million years or more. Current evidence suggests a mix. Some systems are clearly active, others are clearly fossil. Many fall somewhere in between, making it hard to draw firm conclusions. But the more systems we discover and study, the clearer the picture becomes. And one pattern that's emerging is that the largest systems tend to be older, not necessarily in terms of when they formed, but in terms of how long their jets have been active. You don't grow jets 23 million light-years long in 10 million years. You need sustained, stable activity over much longer timescales. This brings us back to the mystery of stability. What allows a black hole to maintain jets pointing in the same direction for tens or hundreds of millions of years? Black holes are messy eaters. The gas falling into them doesn't arrive in a smooth, steady stream. It clumps, swirls, and forms an accretion disk that's constantly changing. Small perturbations can redirect jets. Galaxy mergers can completely disrupt the system. And yet, the existence of systems like Porphyrion proves that somehow, under the right circumstances, jets can remain remarkably stable for immensely long periods. One possibility involves the black hole's spin. A spinning black hole creates powerful magnetic fields in the surrounding accretion disk. These fields can stabilize the jets, keeping them collimated and pointing in a consistent direction, even as the gas flow varies. If the black hole is spinning rapidly, and if the accretion disk is well ordered, the jets might be more stable. But we can't directly measure the spin of black holes in these distant galaxies, so this remains speculative. Another factor might be the environment. If the host galaxy sits in a particularly stable region of the cosmic web, with a steady supply of gas flowing along filaments, the black hole's fuel supply might be more consistent. Fewer disruptions mean fewer opportunities for the jets to be redirected or shut off. And if the intergalactic medium around the galaxy has low density, the jets can propagate more easily without being disrupted by interactions with surrounding gas. Whatever the explanation, the key insight is that giant radio galaxies aren't just scaled-up versions of smaller systems. They require special conditions. Not exotic conditions necessarily, but a fortunate combination of factors that allows the jets to grow to cosmological sizes. And as we continue to discover more of these systems, we're learning that this combination isn't as rare as we once believed. The discovery rate itself tells us something important. Until recently, we knew of only a few hundred giant radio galaxies. Now, thanks to surveys like LOFAR, we've catalogued over 10,000. That's not just a numerical increase. It's a paradigm shift in how common we thought these objects were. Early estimates suggested giant radio galaxies represented a tiny fraction of the radio galaxy population, maybe 1%, maybe less. But those estimates were based on incomplete data. The surveys we used simply weren't sensitive enough to detect the faint, diffuse lobes that characterize many of these systems. We were looking in the wrong way, with the wrong tools. LOFAR changed that. Operating at low radio frequencies, it's specifically designed to detect extended, low surface brightness emission. The kind of emission that previous surveys missed entirely. And when researchers turned LOFAR's gaze to the sky and began processing the data, they didn't just find a handful of new giants, they found thousands. This raises an obvious question. If giant radio galaxies are this common, why didn't we find them earlier? Part of the answer is technological. LOFAR represents a fundamentally different approach to radio astronomy. Traditional radio telescopes use large dishes to collect radio waves. LOFAR uses thousands of small antennas spread across Europe, combining their signals to create extraordinarily sensitive images of the radio sky. This distributed approach makes LOFAR particularly good at detecting large, faint structures that would be invisible to conventional telescopes. But there's another factor: selection bias. When astronomers first started cataloguing radio galaxies, they naturally focused on the brightest, most compact sources. These were easier to detect and study. Over time, this created a skewed picture of what typical radio galaxies looked like. We built our models and theories around these bright, compact objects, unconsciously assuming they represented the full population. Giant radio galaxies, with their vast, faint lobes, didn't fit that picture. They were harder to detect, harder to study, and often dismissed as rare outliers. Only when we specifically went looking for them, with the right tools and the right methods, did we realize how common they actually are. This pattern repeats throughout astronomy. We find what we're equipped to see. Every new instrument reveals phenomena we didn't know existed, forcing us to revise our understanding of how common or rare different cosmic objects actually are. The sheer number of giant radio galaxies now known has another implication. These systems must have been even more common in the past. Remember, we're looking back in time when we observed distant galaxies. The light from Porphyrion left its host galaxy 7.5 billion years ago. Back then, the universe was younger, denser, and more active. Black holes were growing rapidly, fed by abundant gas flowing along the cosmic web. In that environment, giant radio galaxies likely formed more frequently than they do today. The universe has aged and quieted since then. Gas has been used up in star formation or ejected from galaxies by previous generations of jets. The cosmic web has stretched and thinned as space expanded. Conditions today are less favorable for growing giant jets than they were billions of years ago. This means that in the early universe, giant radio galaxies might not have been rare at all. They might have been the norm. And if that's true, their jets had a profound influence on cosmic evolution, shaping the distribution of gas, spreading magnetic fields, and affecting galaxy formation across vast regions of space. Think about what that implies for the intergalactic medium. The space between galaxies isn't truly empty. It contains diffuse gas, primarily hydrogen, with trace amounts of heavier elements. This gas acts as a reservoir for future star formation. When it falls into galaxies, It fuels the creation of new stars. But it's also surprisingly hot, with temperatures in the millions of degrees, and it's magnetized. Weak magnetic fields permeate intergalactic space, their origin long debated. Where did this heat come from? Where did the magnetic fields originate? Jets from giant radio galaxies provide a compelling answer. As jets propagate through the intergalactic medium, they deposit enormous amounts of energy. They accelerate particles to near light speed. They generate magnetic fields. They shock and heat the surrounding gas. A single jet system like Porphyrion can affect a volume of space spanning tens of millions of light years. Multiply that by thousands of similar systems active throughout cosmic history, and you begin to see how jets might have fundamentally shaped the intergalactic medium. Every place in the universe may have been touched by a jet at some point. The heat we observe, the magnetic fields we detect, might be the cumulative legacy of billions of years of black hole activity. This idea gains support from computer simulations. When researchers model the evolution of the universe, including the effects of jets from active black holes, they find that jets are essential for reproducing the observed properties of the intergalactic medium. Without jets, the simulations produce gas that's too cold, too dense, and too prone to forming stars. With jets, the models match observations much better. But here's where things get interesting. Not all jets are created equal. The jets from giant radio galaxies, the ones we've been discussing, are relatively gentle. They're powerful, yes, but they're also old and diffuse. They've been propagating for tens of millions of years, spreading their energy over vast volumes of space. Compare that to jets from quasars. Quasars are the most luminous objects in the universe, powered by black holes that are actively gorging on matter. Their jets are young, compact, and incredibly energetic. They can tear through the interstellar medium of their host galaxies, disrupting star formation and potentially even ejecting gas entirely. These two types of jets have different effects. Quasar jets are like cosmic blowtorches, concentrated and destructive. Giant radio galaxy jets are more like a slow leak of energy into intergalactic space, spread thin, but covering enormous areas. Both play roles in cosmic evolution, but in different ways. Quasar jets affect their host galaxies directly, regulating star formation and potentially limiting the growth of the galaxy itself. Giant radio galaxy jets affect the larger scale environment, heating the intergalactic medium and spreading magnetic fields across the cosmic web. Understanding which type of jet dominates at different epochs in cosmic history is crucial for understanding how the universe evolved. In the early universe, when black holes were growing rapidly and galaxies were merging frequently, quasar jets were likely more common. As the universe aged and settled down, the balance may have shifted toward the more diffuse jets we see in giant radio galaxies. This brings us back to Porphyrion and systems like it. Porphyrion existed when the universe was less than half its current age. It was a time of transition. Black holes had already grown to enormous sizes, but the universe was still dense enough and active enough to fuel their jets. Porphyrion represents a sweet spot, a moment in cosmic history when conditions were just right for growing the largest jets the universe has ever seen. Will we find larger ones? Almost certainly. TXS 0033+252, discovered in 2024, already surpasses Porphyrion with jets spanning 26 million light-years. As surveys continue and our detection methods improve, we'll likely find even more extreme examples. But there's probably a practical limit. Jets can't grow indefinitely. At some point, the jet's energy dissipates faster than it can be replenished. The intergalactic medium, however thin, exerts drag on the expanding lobes. The black hole's fuel supply eventually runs low or gets disrupted, and the universe itself is expanding, which affects the growth rate of jets over cosmological timescales. Current models suggest that jets might reach maximum sizes of around 30 to 40 million light-years before these limiting factors shut down further growth. We're already seeing systems approaching these scales. Whether anything substantially larger exists remains to be discovered. The technology to find these objects keeps improving. LOFAR was revolutionary, but it's not the final word. The Square Kilometre Array, currently under construction in Australia and South Africa, will be even more sensitive. It will detect fainter structures, probe deeper into cosmic history, and potentially reveal populations of giant radio galaxies we haven't yet imagined. And there are other ways to study these systems beyond just imaging their radio emission. Gravitational lensing can reveal the distribution of mass along the jets, helping us understand how they interact with dark matter. X-ray observations can detect hot gas shocked by the jet's passage. Optical spectroscopy can measure the velocities and compositions of gas clouds entrained by the jets. Each technique adds another piece to the puzzle. The more we learn, the clearer the picture becomes. But also the more questions arise. That's how science works. Every answer opens new avenues of inquiry. For instance, we now know that giant radio galaxies can form from radiative mode black holes, like the one powering Porphyrion. This was unexpected. We thought only jet mode black holes, which derive most of their energy from the spin of the black hole rather than radiation from the accretion disk, could produce such large jets. Porphyrion proves otherwise, and if radiative mode black holes can produce giant jets, that expands the population significantly. Radiative mode black holes are far more common than jet mode ones, especially in the early universe. This means the impact of giant jets on cosmic evolution might be even greater than we thought. It also means we need to rethink our models of how jets form and how they're powered. The distinction between radiative mode and jet mode black holes might not be as clear-cut as we assumed. Perhaps there's a spectrum of behaviors, with black holes transitioning between modes depending on their fuel supply and environment. The more we study these systems, the more we realize how much we still don't understand. And giant radio galaxies have something else to teach us about cosmic history. Their distribution across time reveals patterns we didn't anticipate. When astronomers map giant radio galaxies by redshift, which translates to cosmic epoch, something peculiar emerges. These systems aren't evenly distributed through time. There are distinct periods when they appear more frequently, and other epochs where they're surprisingly rare. Why? The answer lies in the cosmic web's evolution. Remember, dark matter forms the scaffolding of the universe, creating filaments along which gas flows and galaxies form. This structure changes over time. In the early universe, the cosmic web was denser, more compact. Filaments were closer together. As the universe expanded, this structure stretched and thinned. Giant radio galaxies seem to track this evolution in unexpected ways. During certain epochs, the space in between filaments hit a sweet spot. Jets could extend far enough to cross significant portions of the cosmic void between filaments. injecting energy and magnetic fields into these regions. This had profound effects on the intergalactic medium. The gas between galaxies isn't just sitting there passively. It's dynamic, influenced by radiation, winds from stars, and most dramatically, by jets from active galactic nuclei. When a jet plows through the intergalactic medium, it heats the gas. A lot. Temperatures can reach millions of degrees. This heated gas becomes less likely to collapse and form new stars. In dense regions like galaxy clusters, this feedback mechanism might explain why we don't see as much star formation as simulations predict. The black holes are regulating their own food supply, heating the very gas that would eventually feed them. But giant radio galaxies operate on larger scales than cluster-confined jets. Their reach extends across the cosmic web itself. They heat gas in regions that would otherwise be pristine, unaffected by galactic activity. This could explain observations showing that even gas in cosmic voids, the empty spaces between filaments, shows signs of heating and magnetization. Giant jets might be responsible. Here's where it gets fascinating. If every location in the universe has been touched by jet activity at some point in cosmic history, that changes our understanding of structure formation. The intergalactic medium isn't a blank slate. It's been pre-processed, heated, magnetized by countless jets over billions of years. This affects how gas collapses to form new galaxies, how stars form within those galaxies, and ultimately, how the cosmic web itself evolves. Some researchers now believe giant radio galaxies might be the primary source of magnetic fields in the universe. Magnetic fields are everywhere. We detect them in galaxies, in the intergalactic medium, even in cosmic voids. But where did they come from originally? Theories vary, but jets offer a compelling explanation. They carry magnetic fields generated near black holes and spread them across cosmological distances. Over time, these seed fields get amplified by turbulence and galactic activity, growing into the magnetic structures we observe today. Testing this hypothesis requires studying giant radio galaxies at different cosmic epochs. Do we see stronger magnetic fields in regions that have been swept by jets compared to regions that haven't? Initial results suggest yes. Areas crossed by giant jets show enhanced magnetic field strength and specific patterns consistent with jet interactions. But we need more data. The sample size of well-studied giant radio galaxies remains relatively small, especially at high redshifts. That's changing. Recent surveys have uncovered thousands of giant radio galaxies. The LOFAR 2-meter sky survey alone found over 8,000 new ones, dramatically expanding the known population. And many of these are at high redshifts, allowing us to probe earlier cosmic epochs. Each discovery adds another data point, another piece of the puzzle. But quantity alone isn't enough. We need detailed follow-up observations. Radio surveys give us the broad structure, the overall size and morphology of jets. But to understand what's happening physically, we need multi-wavelength observations. X-rays reveal hot gas shocked by the jet's passage. Optical spectroscopy measures gas velocities and chemical compositions. Infrared observations probe dust heated by jet interactions. Each wavelength tells a different part of the story. Consider ASCAP J0107-2347, discovered by the Australian Square Kilometre Array Pathfinder. This giant radio galaxy, located about 1.5 billion light-years away, displays something remarkable. It has two sets of radio lobes, one nested inside the other. The inner lobes are bright and compact. The outer lobes are faint and elongated, stretching over 12 million light-years. This nested structure suggests episodic activity. The black hole didn't just turn on once and stay on. It went through multiple active phases, separated by periods of quiescence. During the first active phase, it produced the inner lobes. Then it shut down. The jets stopped flowing, and the inner lobes began to fade. Later, perhaps millions of years later, the black hole reactivated. New jets formed, creating the outer lobes, while the remnants of the inner ones remained visible. Why does the black hole's activity cycle like this? Probably because its fuel supply is irregular. Black holes don't have steady streams of gas falling into them. The accretion process is chaotic, influenced by galactic dynamics, mergers, interactions with other galaxies. Gas flows toward the black hole in bursts, triggering active phases. When the supply runs low, the activity ceases. Then another burst of gas arrives, and the cycle repeats. This episodic behavior might explain how some giant radio galaxies reach such enormous sizes. If jets operated continuously, they'd eventually push away all the surrounding gas, cutting off their own fuel supply. But with episodic activity, there's time for gas to replenish between active phases. The jets can grow larger over multiple cycles than they could in a single continuous episode. Other giant radio galaxies show similar nested structures, suggesting episodic activity is common. This has implications for understanding black hole growth. If supermassive black holes accrete in bursts rather than steadily, that affects how quickly they grow and how they influence their host galaxies. It also affects the total energy output over cosmic time. An episodic black hole produces less total energy than a continuously active one, but it spreads that energy over longer timescales and larger volumes. Now let's talk about IC1101. This galaxy represents a completely different approach to being large. While Porphyrion and Alcyoneus achieved their size through radio jets, IC1101 is genuinely enormous in terms of stellar mass. It's a supergiant elliptical galaxy with a diameter of roughly 4 to 6 million light-years, depending on how you measure it. That's 40 times the diameter of the Milky Way. IC1101 sits at the center of the Abell 2029 galaxy cluster, located about 1.15 billion light-years away. It contains an estimated 100 trillion stars. To put that in perspective, the Milky Way has between 200 and 400 billion stars. IC1101 contains 250 times more stars than our entire galaxy. If you try to count them at a rate of 1 per second, it would take over 3 million years. How did IC1101 become so massive? Through galactic cannibalism. It's the dominant galaxy in a rich cluster, meaning it's surrounded by hundreds of other galaxies. Over billions of years, IC1101's gravity has pulled in and consumed dozens, possibly hundreds of smaller galaxies. Each merger added mass, making IC1101 progressively larger and more massive. But here's the catch. All those mergers stripped away star-forming gas. When galaxies collide, their gas clouds smash together, triggering intense bursts of star formation. But much of that gas gets heated to such high temperatures that it can't collapse to form new stars. It becomes part of the hot intracluster medium, the diffuse gas filling the space between galaxies in the cluster. IC1101, despite its enormous size, forms very few new stars. It's essentially dead, composed of old red and yellow stars with almost no young blue stars. This is typical for giant elliptical galaxies in cluster centers. They grow through mergers, but those same mergers shut down star formation. They become massive but quiescent, dominated by aging stellar populations. IC1101's core is particularly interesting. It spans over 13,000 light-years, making it the largest galactic core ever observed. That's roughly 10 times larger than typical elliptical galaxy cores. This diffuse core probably formed through repeated mergers that scattered stars outward, preventing them from settling into a compact configuration. At the heart of IC1101 lurks a supermassive black hole. Its mass isn't precisely measured, but estimates suggest tens of billions of solar masses. That's among the most massive black holes known. Yet IC1101 isn't a radio galaxy. Its black hole isn't actively producing jets, at least not currently. It might have been active in the past, but it's quiescent now, starved of fuel after billions of years of growth. Comparing IC1101 to Porphyrion highlights the different ways galaxies can be large. IC1101 is large in stellar content, mass, physical extent measured by stars. Porphyrion is large in terms of its sphere of influence, the volume affected by its jets. Both are products of their environments. IC1101 grew in a dense cluster where mergers are common. Porphyrion's jets grew in a relatively low-density region where resistance was minimal. Neither is more legitimate than the other as the largest galaxy. They're measuring different things. It's like asking whether Russia or Canada is larger. By land area, Russia wins. By total area, including territorial waters, Canada might win depending on definitions. The answer depends on what you're measuring. Similarly, the largest galaxy depends on whether you prioritize stellar content or sphere of influence. This definitional ambiguity frustrates some astronomers, but delights others. It reveals the complexity of cosmic structure, the multiple ways objects can be extreme, and it forces us to think carefully about what we mean by size. In everyday life, size is straightforward. A person's height is measurable with a ruler, but galaxies don't have sharp edges. Their stellar density fades gradually. Their jets extend far beyond visible structures. Defining where a galaxy ends and intergalactic space begins is surprisingly subjective. Most astronomers use the half-light radius for stellar measurements. This is the radius containing half the galaxy's total light. It's objective, reproducible, and doesn't depend on telescope sensitivity. But it underestimates the galaxy's true extent. Faint outer regions contribute little light, but still contain stars. For radio galaxies, astronomers measure the extent of radio emission above a certain threshold, but that threshold is arbitrary. Lower thresholds reveal larger structures. Higher thresholds give smaller sizes. Despite these challenges, the quest to find the largest galaxies continues. It's not just about bragging rights. These extreme objects test our theories. They reveal processes operating at maximum intensity, pushed to their limits. Understanding how they form and evolve helps us understand galaxy formation in general, and they connect us to the universe's history in profound ways. When we look at Porphyrion's jets spanning 23 million light-years, we're witnessing something that happened 7.5 billion years ago. The universe was younger then, smaller, more densely packed. The cosmic web's filaments hadn't stretched as far apart as they have today. This matters more than you might think. Porphyrion's jets don't just extend through empty space, they pierce through the cosmic web itself, those vast filaments of dark matter and gas that connect galaxies. At the epoch when Porphyrion was active, these filaments were closer together. The jets could reach farther as a proportion of the universe's structure. Calculations show Porphyrion's jets span roughly 2/3 the distance across cosmic voids at that time. Voids are the empty regions between filaments, the least dense parts of the universe. 2/3 of a void's diameter. That's genuinely cosmological scale. These jets aren't just affecting their host galaxy or nearby neighbors. They're influencing structure on scales comparable to the largest features in the universe. What does that influence look like? Jets carry enormous energy. When they plow through intergalactic gas, they heat it, magnetize it, stir it. This affects how gas can cool and collapse to form new galaxies. It might suppress star formation in some regions while triggering it in others. The energy injection is so vast that it can alter the evolution of entire galaxy clusters. But Porphyrion's reach extends beyond even that. Recent observations suggest these giant jets might be responsible for magnetizing the intergalactic medium on the largest scales. The universe's magnetic fields aren't random. They show structure, coherence across vast distances. Where did those magnetic fields come from? One possibility, jets like Porphyrions. As jets propagate through space, they carry magnetic fields with them. They twist and amplify those fields. When the jets eventually fade, the magnetic fields remain, threaded through the cosmic web. Multiply this by millions of giant radio galaxies over billions of years, and you might explain the widespread magnetization we observe. This changes how we think about galaxy evolution. We've known for decades that supermassive black holes and their host galaxies co-evolve. The black hole's mass correlates with properties of the galactic bulge. This suggests a feedback mechanism. The black hole affects the galaxy, and the galaxy affects the black hole. But if jets can influence regions far beyond their host galaxy, then this feedback operates on much larger scales than previously thought. A black hole in one galaxy could affect the evolution of galaxies millions of light years away. The cosmic web becomes a network not just of matter, but of influence, with black holes as nodes that shape their surroundings across vast distances. Porphyrion also challenges our understanding of black hole activity modes. Most giant radio galaxies are powered by what astronomers call jet mode accretion. The black hole accretes matter relatively slowly. It's efficient at launching jets but doesn't produce much radiation. The galaxy appears dim in visible light but bright in radio wavelengths. Porphyrion is different. Its host galaxy shows signs of radiative mode accretion. The black hole is consuming matter rapidly, producing copious radiation. This is the mode associated with quasars, the brightest objects in the universe. Astronomers didn't think radiative mode black holes could produce such enormous jets. The discovery forced a rethink. Clearly they can, and if Porphyrion isn't unique, if other radiative mode systems produce giant jets, then we've been missing a major population of influential objects. Quasars are common in the distant universe. If many of them produce jets like Porphyrions, the implications for cosmic evolution are profound. Why didn't we detect these jets earlier? Sensitivity. Porphyrion's jets are faint. They emit radio waves at low frequencies, which are difficult to observe. Ground-based telescopes struggle with interference from Earth's ionosphere. Early radio surveys lacked the sensitivity to detect such diffuse emission. LOFAR changed that. The low-frequency array uses thousands of small antennas spread across Europe. By combining their signals, it achieves both high sensitivity and good resolution. It can detect faint, extended structures that previous surveys missed. The result? Over 10,000 giant radio galaxies discovered in LOFAR data. Porphyrion is just the largest, but the population is vast, far larger than anyone expected. Giant radio galaxies aren't rare oddities. They're common features of the universe, at least in its past. This abundance matters. If giant jets were rare, they'd be curiosities, extremes that don't significantly affect cosmic evolution. But if they're common, if thousands or millions existed throughout cosmic history, they're a major factor in shaping the universe we see today. Consider the energy budget. Each giant radio galaxy pumps energy equivalent to trillions of suns into the intergalactic medium over its lifetime. Multiply by millions of such systems over billions of years. The total energy is staggering. It rivals the energy released by all supernovae combined. Yet we've only recently begun to account for this energy source in models of galaxy formation. Previous simulations either ignored it or treated it as a minor correction. Now it's clear that jet feedback from giant radio galaxies must be included as a primary mechanism shaping cosmic structure. But here's what keeps astronomers awake at night. We still don't fully understand how these jets work. The basic picture is clear. Matter falls toward the supermassive black hole, forming an accretion disk. Magnetic fields in the disk get twisted and amplified. Eventually, they launch jets of plasma along the black hole's rotation axis. The details are murky. How exactly do magnetic fields launch jets? What determines the jet's speed, power, direction? Why do some black holes produce strong jets while others don't? We have partial answers, theoretical frameworks, computer simulations, but we lack complete understanding. And the stability question looms large. Porphyrion's jets extend 23 million light-years. Light takes 23 million years to cross that distance. The jets themselves probably took hundreds of millions of years to grow that large, maybe a billion years. During that time, the black hole's accretion rate must have remained relatively stable. The jets must have kept pointing in the same direction. Any significant wobble would create curved jets, kinked structures. Porphyrion's jets are remarkably straight. What keeps them stable? The black hole's spin provides one anchoring mechanism. If the black hole spins rapidly, its rotation axis defines a stable direction. Magnetic fields threading the accretion disk lock into this direction. The jets follow, but accretion disks aren't perfectly stable. They can wobble, precess, change orientation. The black hole itself can be jostled by gravitational interactions with passing stars or dark matter clumps. Any of these perturbations should deflect the jets, at least slightly. Yet Porphyrion's jets show no significant deflection over their entire length. This implies extraordinary stability, both in the black hole's accretion and in the surrounding environment. The cosmic web filament in which Porphyrion's host galaxy is embedded must have remained relatively undisturbed for hundreds of millions of years. This tells us something important about the cosmic web's evolution. Filaments aren't static. They grow, merge, fragment. Galaxies move along them. But the timescales involved are long enough that on scales of hundreds of millions of years, a filament can provide a stable environment for jet growth. Now consider what happens as the universe continues expanding. space itself stretches, carrying galaxies farther apart. The cosmic web's filaments grow longer, thinner, more diffuse. The distance between nodes increases. This has consequences for giant radio galaxy formation. As the universe ages, the environment becomes less favorable for producing ultra-giant jets. There's less gas to plow through, less resistance to collimate the jets, more space for them to dissipate. This might explain why giant radio galaxies like Porphyrion seem more common in the distant past. The universe was denser then. Conditions favored jet growth to extreme sizes. Today, in the local universe, giant radio galaxies still form, but they don't reach the same proportions. Alcyoneus, at 16 million light-years, is enormous by modern standards, but it's smaller than Porphyrion, and Alcyoneus exists in the relatively nearby universe, only 3.5 billion light-years away. Porphyrion, at 7.5 billion light-years distance, existed when the universe was younger and denser. This creates a selection effect. The largest giant radio galaxies we can observe come from earlier epochs. By the time their light reaches us, they're ancient history. We're seeing them as they were, billions of years ago. What happened to them since? Have their jets faded? Did their host galaxies merge with others? We don't know. Following up on these systems is challenging. Their host galaxies are faint, distant dots. Measuring their properties requires powerful telescopes and long observation times. Determining whether the jets are still active or have shut off demands multi-wavelength observations across the electromagnetic spectrum. Recent studies using the giant meter-wave radio telescope in India, combined with optical data from the Dark Energy Spectroscopic Instrument, have started filling in these details. For Porphyrion, they've confirmed the host galaxy is massive, about 10 times the Milky Way's mass. Its black hole is actively accreting, producing radiation as well as jets. But many questions remain. What triggered the black hole's activity? Was it a galaxy merger that funneled gas toward the center? Or did the galaxy simply capture gas from the cosmic web, providing steady fuel for the black hole? The answer matters for understanding galaxy evolution. If mergers are the primary trigger, then giant radio galaxies should preferentially occur in regions with high galaxy densities, where mergers are common. If cosmic web accretion is sufficient, then giant radio galaxies could form anywhere along filaments, regardless of local galaxy density. Current observations show both scenarios occurring. Some giant radio galaxies reside in galaxy clusters, where mergers are frequent. Others, like Alcyoneus, are relatively isolated, suggesting cosmic web accretion. This diversity indicates multiple pathways to giant jet formation. It also suggests that the largest galaxies, whether measured by stellar content or sphere of influence, aren't products of a single formation mechanism. They're outcomes of various processes operating under different conditions. The universe is more creative than our theories sometimes give it credit for. And there's another wrinkle. The largest galaxies we've discovered might not be the largest that exist. Our surveys have limitations. Radio telescopes have finite sensitivity. They can only detect jets above a certain brightness threshold. Fainter jets remain invisible. If there are giant radio galaxies with jets even larger than Porphyrion's but correspondingly fainter, we wouldn't see them with current technology. They'd slip through our surveys undetected, waiting for more sensitive instruments. This isn't idle speculation. Every time we improve our observational capabilities, we find larger structures than we expected. LOFAR revealed Alcyoneus, which seemed impossibly large when first discovered. Then further analysis of LOFAR data revealed Porphyrion, even larger. More recently, TXS 0033 plus 252 was identified, potentially larger still at 26 million light-years, though its measurement remains somewhat uncertain pending further observations. The pattern is clear. Our conception of the largest galaxies keeps expanding as our tools improve. This suggests we haven't reached the true limit yet. There might be even more extreme systems waiting to be discovered. Jets that span 30, 40, 50 million light-years or more. At some point, physical limits must intervene. Jets can't grow indefinitely. They eventually dissipate as they plow through the intergalactic medium, their energy spreading out until the coherent beam structure breaks down. The cosmic web's density sets a practical limit. Too little gas, and jets can't remain collimated. Too much, and resistance slows jet growth. But we don't know precisely where that limit lies. The largest jets we've found might be approaching it, or they might be nowhere close. Only further observations will tell. The question becomes, what will next-generation instruments reveal? The square-kilometre array, currently under construction in Australia and South Africa, will dwarf LOFAR's sensitivity. It'll detect radio signals hundreds of times fainter than current surveys can see. If giant jets exist beyond TXS 0033 plus 252, the SKA should find them, and if it doesn't, that would tell us something equally important. It would suggest we've reached the natural limit, that jets simply can't maintain coherence beyond roughly 30 million light-years. Either outcome reshapes our understanding. But there's a deeper implication here that goes beyond cataloguing ever larger structures. These giant radio galaxies are telling us something fundamental about how black holes influence the universe. For decades, astronomers focused on black holes' effects within their host galaxies. Jets inject energy into surrounding gas, heating it, preventing it from cooling and forming new stars. This feedback mechanism helps explain why the most massive galaxies stopped forming stars billions of years ago. Their central black holes essentially turned off star formation by making the gas too hot to collapse. That picture worked well for explaining individual galaxies. But Porphyrion changes the scale. Its jets don't just affect its host galaxy. They reach across cosmic voids, injecting energy and magnetic fields into regions that contain nothing but diffuse intergalactic gas. This gas comprises most of the universe's normal matter. We can barely detect it because it's so spread out, so hot, so diffuse. Yet it matters enormously for cosmology. Its distribution, temperature, and magnetization affect how galaxies form, how they cluster, how the cosmic web evolves. Porphyrion's jets are pumping energy into this medium on scales comparable to the cosmic web itself. That means black holes aren't just local phenomena, they're cosmic architects shaping the large-scale structure of the universe. This realization forces a rethinking of galaxy evolution models. Previous simulations included black hole feedback within galaxies, but largely ignored its effects on the intergalactic medium beyond immediate surroundings. Porphyrion suggests that's inadequate. Jets like these can magnetize the cosmos, heat the voids, alter the flow of gas along filaments. Why does magnetization matter? Because magnetic fields affect how gas moves and cools. They provide pressure support against gravity, potentially slowing structure formation. They also accelerate cosmic rays to enormous energies, creating the diffuse radiation we detect throughout the universe. If giant jets are responsible for seeding magnetic fields across cosmic scales, that explains why the intergalactic medium is magnetized at all. Without some mechanism to spread magnetic fields, they'd remain concentrated near galaxies where they're generated. Jets provide that mechanism, carrying fields outward like cosmic irrigation systems. This connects to another mystery: cosmic rays. These high-energy particles bombard Earth constantly, arriving from all directions with energies far exceeding anything we can produce in accelerators. Where do they come from? Some originate in supernovae. Others might come from exotic sources like evaporating black holes or colliding dark matter. But the highest energy cosmic rays likely get accelerated in environments with strong magnetic fields and powerful shocks. Giant radio jets fit that description perfectly. The shock fronts where jets slam into intergalactic gas could accelerate particles to extreme energies, then scatter them throughout space. If that's correct, then every region of the universe has likely been touched by jets at some point. Porphyrion's jets reach 2/3 of the way across cosmic voids. During the early universe, when the cosmic web was more compressed, jets could span even larger fractions of void space. And there were more active black holes back then, meaning more jets. The cumulative effect might have magnetized and energized the entire observable universe. Every atom floating between galaxies might carry a faint signature of ancient jet activity, a memory of when black holes were more violent, more active, more influential. This raises a provocative question. Did giant jets play a role in galaxy formation itself? The cosmic web formed from initial density fluctuations in the early universe. Dark matter collapsed first, creating gravitational wells that attracted normal matter. Gas flowed along filaments, eventually gathering in dense nodes where galaxies formed. Standard models treat this process as primarily gravitational. But if jets were injecting energy into the intergalactic medium during this epoch, they could have altered the process. They might have prevented gas from cooling in some regions, delaying galaxy formation, or they might have compressed gas in others, triggering star formation earlier than expected. We don't have definitive evidence yet, but simulations are starting to include these effects. Early results suggest jets could indeed alter the galaxy formation process, particularly in dense environments where many active black holes existed. If confirmed, it means black holes weren't passive players in cosmic evolution. They actively shaped the distribution of galaxies we see today. Now, here's where the story circles back to IC 1101 and the stellar giants. Those massive elliptical galaxies form through different processes than radio giants like Porphyrion. They grew by mergers, accumulating stars rather than projecting jets, yet they're connected. IC 1101 sits at the center of a galaxy cluster where mergers are common. Its supermassive black hole likely underwent multiple feeding episodes as galaxies fell in and merged. Some of those episodes probably produced jets, though we don't see them today. The black hole is currently quiescent, having consumed its available fuel, but in its active past, IC 1101's black hole might have driven jets comparable to modern giants. Those jets would have affected the cluster's intracluster medium, heating it, stirring it, preventing cooling flows. The fact that IC 1101 stopped forming stars billions of years ago suggests something shut down star formation. Black hole feedback is the leading explanation. Jets and radiation from the central black hole heated gas throughout the galaxy, making it too hot to form new stars. The same process might operate in all massive ellipticals, so there's a continuity here. Giant radio galaxies show us black holes actively shaping their surroundings through jets. Massive ellipticals show us the aftermath, galaxies where black hole feedback has already done its work. Both represent extremes. Porphyrion's jets are exceptionally large, but relatively typical in their effects. IC 1101's stellar mass is exceptional, but achieved through common merger processes. Together, they bracket the range of galactic extremes. Yet both remain dwarfed by the cosmic web itself. The filaments connecting galaxy clusters span hundreds of millions of light years. The voids between filaments stretch even farther. Even Porphyrion's 23 million light-year jets are small compared to these larger structures. This puts things in perspective. The biggest individual galaxies, whether measured by stars or jets, are still just components of larger systems. They're nodes in the cosmic web, influential but not dominant. That said, their influence might be more pervasive than their size suggests. If giant jets magnetize the universe, if they seeded cosmic rays throughout space, if they altered galaxy formation across cosmic scales, then they've left fingerprints everywhere. Every structure we see might carry traces of their activity. The challenge is detecting those traces, distinguishing jet effects from other processes. One approach involves studying the polarization of radio waves from distant galaxies. Magnetic fields cause radio emission to become polarized, with waves oscillating in preferred directions. By mapping polarization across the sky, astronomers can trace magnetic field structures. If those structures align with known jets or show patterns consistent with ancient jet activity, that provides evidence for jets' cosmic influence. Early results show some correlations, but the data remains noisy. More sensitive observations are needed. Another approach examines the intergalactic medium's temperature. Jet heating should leave signatures in the gas, raising its temperature in regions where jets once passed. X-ray telescopes can detect this hot gas, though it's extremely faint. Comparing observed temperatures to simulations helps constrain how much energy jets injected. Again, results are promising, but not yet conclusive. The coming decade should clarify these questions. New instruments are coming online specifically designed to probe the intergalactic medium. The SKA will revolutionize radio astronomy. Next-generation X-ray telescopes will map hot gas with unprecedented precision. Optical surveys will identify millions more galaxies, providing statistical power to detect subtle jet effects. Together, these tools should reveal whether giant jets truly shape the cosmos or merely represent spectacular but localized phenomena. What we've learned already is humbling. The largest galaxies challenge our assumptions repeatedly. They're larger than we expected, form through more diverse processes than we predicted, and influence broader regions than we imagined. Each discovery expands our conception of what's possible. Each new record holder forces us to revise our models. The universe keeps surprising us because we keep looking closer, deeper, more carefully than before. And there's no reason to think we've seen the limits yet. Technology improves, techniques refine, theories evolve. What seems impossibly large today might seem modest in a decade. The next generation of astronomers will discover structures that dwarf Porphyrion, phenomena that make IC 1101 seem ordinary. That's how science progresses, through constant expansion of the known, relentless pushing against boundaries. For now, we're left with a universe more vast and interconnected than previous generations imagined. Black holes at galactic centers aren't isolated objects. They're cosmic influences, projecting power across millions of light years, shaping the medium between galaxies, potentially affecting structure formation throughout the observable universe. The largest galaxies, whether defined by stars or influence, represent extreme endpoints of processes operating everywhere. They're laboratories for understanding how galaxies grow, how black holes evolve, how the cosmos itself develops structure from initial formless chaos. Every time you look at the night sky, you're seeing the products of these processes. The galaxies visible in telescopes formed within the cosmic web, fed by gas flowing along filaments, regulated by black hole feedback. Some grew massive through mergers, like IC 1101. Others project influence through jets, like Porphyrion. Most do both at different times, cycling through active and quiescent phases as their black holes feed and starve. We're fortunate to live in an era when we can study these objects. A century ago, we didn't know galaxies existed beyond our own. 50 years ago, we'd barely begun measuring their properties. Today, we can detect jets spanning 20+ million light-years in galaxies billions of light-years away. We can trace their effects on the intergalactic medium, reconstruct their histories, predict their futures. That's an extraordinary achievement, a testament to human curiosity and ingenuity. The largest galaxies remind us that the universe operates on scales beyond immediate intuition. They force us to think bigger, to consider interconnections spanning cosmic distances, to recognize that local and global aren't separate categories, but points on a continuum. What happens in one galaxy affects its neighbors. What happens in galaxy clusters affects the cosmic web. Everything connects. Everything influences everything else. Across distances that light takes millions of years to traverse. That's the real lesson from these cosmic giants. Size matters, but influence matters more. The largest galaxies aren't just impressive because they're big. They're important because they reveal how the universe works at fundamental levels, how structure emerges from chaos, how black holes shape galaxies, how galaxies shape the cosmos. Understanding them helps us understand everything. The largest galaxies we've discovered aren't endpoints. They're waypoints in an ongoing process of cosmic revelation. Every time we build a more sensitive instrument, we find structures that exceed what we thought was possible. LOFAR revealed thousands of giant radio galaxies that previous surveys missed entirely. The square-kilometre array will push those boundaries further. What seems impossibly large today becomes merely impressive tomorrow. This pattern tells us something profound about the nature of scientific discovery. We don't just find what's there, we find what we're equipped to see. Our understanding of the universe expands in lockstep with our technological capabilities. The largest galaxies aren't getting bigger. Our ability to detect them is improving, which raises an uncomfortable question. What else are we missing? Consider what we've learned. Porphyrion stretches 23 million light-years, its jets reaching 2/3 across cosmic voids when the universe was younger and denser. TXS 003 3+252 potentially exceeds that at 26 million light-years, though measurements remain uncertain. IEC 1101 contains 100 trillion stars in a structure spanning up to 6 million light-years. Each represents extremes in different categories. Each challenges our definitions of what makes a galaxy large. But definitions matter less than understanding. These objects aren't just cosmic curiosities. They're active participants in universal evolution. Porphyrion's jets didn't merely exist in isolation. They pumped energy and magnetic fields into the intergalactic medium across distances that dwarf individual galaxies. They heated gas that would otherwise cool and form stars. They magnetized regions that might have remained field-free. They connected filaments of the cosmic web that seemed separate. Multiply that influence by thousands or millions of similar systems throughout cosmic history, and you begin to see why these discoveries matter. Black holes aren't passive consumers of matter. They're cosmic regulators, thermostats controlling the temperature and properties of the space between galaxies. Jets from supermassive black holes shaped the universe we observe today. The intergalactic medium's temperature, its magnetization, its ability to form new galaxies, all carry fingerprints of ancient jet activity. This changes how we think about galaxy evolution fundamentally. We used to imagine galaxies as isolated islands, evolving mostly through internal processes. Mergers happened, gas fell in from surroundings, stars formed and died. But the picture was local, confined to individual galaxies, or at most their immediate neighborhoods. Giant radio galaxies demolish that picture. They show that galaxies are connected across vast distances through jets that carry influence far beyond their host systems. Every place in the universe may have been touched by jet activity at some point. That's not hyperbole. If giant radio galaxies were common in the early universe, and if their jets regularly spanned significant fractions of cosmic voids, then their collective influence covered essentially all of space. The gas floating between galaxies today might carry thermal and magnetic signatures from jets that shut off billions of years ago. The universe has a memory. It remembers when black holes were more active, more violent, more influential. Understanding these systems also reveals limits to our knowledge. We still don't fully understand how jets form, what determines their power, why they remain stable for hundreds of millions of years. The basic physics is clear. Magnetic fields near spinning black holes launch plasma outflows, but the details remain murky. Every new discovery, like Porphyrion, adds constraints, narrowing the range of possible mechanisms. Eventually, we'll converge on a complete theory. But we're not there yet. The nested structure in ASCAP J0107-2347 hints at episodic activity, jets turning on and off as the black hole's fuel supply fluctuates. This might explain how some systems grow to extreme sizes. Instead of one continuous active phase, multiple shorter bursts, separated by quiet periods, allow jets to extend farther than steady accretion would permit. Each cycle adds another layer, building up the structure over cosmic time. IC 1101 represents a different extreme but connects to the same underlying processes. Its massive stellar content resulted from countless mergers, each adding stars while stripping away star-forming gas. Black hole feedback likely played a role, heating gas to prevent new star formation once the galaxy reached sufficient size. The same feedback mechanism operating through jets in radio galaxies operates through radiation and winds in massive ellipticals, different manifestations of the same basic process. black holes regulating their own growth and their host galaxies' evolution. Which brings us back to the question of definition. What makes a galaxy large? If we measure stellar content, IC 1101 wins with its 100 trillion stars. If we measure sphere of influence, Porphyrion wins with jets spanning 23 million light-years. If we measure total mass including dark matter, the largest galaxies might be completely invisible. Their stellar components too faint to detect, but their gravitational influence unmistakable. Each definition gives different answers because galaxies are complex, multi-component systems that defy simple categorization. Perhaps the better question is, what do the largest galaxies teach us? They reveal processes operating at maximum intensity. They show us the universe pushed to extremes. They test theoretical limits and force us to expand our models. Whether through stellar accumulation or jet production, these systems represent what's possible when cosmic processes run to completion uninterrupted. They also remind us of scale. Porphyrion's jets span distances that light takes 23 million years to cross. If you could shrink the jets to the length of a football field, Earth's entire orbit around the Sun would be smaller than a grain of sand. The Milky Way would be about 5 inches long. Human intuition fails at these scales. We can calculate, measure, map these structures, but truly comprehending their size exceeds our evolved cognitive abilities. We're pattern-seeking creatures adapted to navigate environments measured in meters, trying to understand structures measured in megaparsecs, yet we persist. That's perhaps the most remarkable part of this story. Humans, confined to a small planet orbiting an ordinary star, have developed tools and techniques to detect and measure structures millions of light-years across billions of light-years away. We've traced the evolution of galaxies from the early universe to the present. We've identified the processes that shape them. We've connected black holes at galactic centers to the large-scale structure of the cosmos itself. The largest galaxies represent pinnacles of this understanding. They're not just objects to catalogue and measure. They're laboratories for testing ideas about how the universe works at fundamental levels. Every new discovery adds pieces to an incomplete puzzle. Every improved measurement refines our models. Every unexpected finding forces us to think more carefully about assumptions we'd taken for granted. What comes next? More sensitive instruments will find fainter structures. The square-kilometer array will revolutionize radio astronomy within the decade. Next-generation X-ray telescopes will map the intergalactic medium in unprecedented detail. Optical surveys will identify billions of galaxies, providing statistical power to detect subtle trends and correlations. Together, these tools should answer current questions while raising new ones we haven't yet imagined. Will we find jets larger than TXS 0033 plus 252? Probably. Will those discoveries reveal new physics or confirm existing theories? Unknown. Will the largest stellar galaxies turn out to be even more massive than IC 1101? Possibly. The universe has consistently surprised us by exceeding expectations. There's no reason to think that pattern will end. But perhaps the most important realization is simpler. The largest galaxies show us that the universe is vast beyond human comprehension.